Okay, so this is my video for standard 0.3, which has to do with checking our linear algebra skills. It asks us, so the question I chose was number 2, which asks us to show that the trace of a 2 by 2 matrix is the sum of its eigenvalues, and that the determinant of a 2 by 2 matrix is the product of its eigenvalues. So I've gone ahead and written out a general 2 by 2 matrix right here. And for the rest of the video, I'll be referring to this matrix as A. So let's go ahead and find this matrix's eigenvalues. So to do that, we need to take advantage of this equation, which basically you get by manipulating the expression A lambda equals lambda V, where V is one of the matrix's eigenvectors, but that's a proof for another time. So then when we evaluate the determinant of A minus lambda I, which is right here, we end up with this, which is the characteristic equation of lambda. And solving this equation for lambda will give us the eigenvalues. So I've pointed out some suggestive values, some suggestive terms rather, in this equation. And those are the A plus D term, which happened to be the trace of A, and the AD minus BC term, which happens to be the determinant of A. So let's just go ahead and substitute those in. And this is actually pretty much the key step. Noticing that is the key step in this proof. So now let's solve. Notice that this is a quadratic equation in lambda, so we can solve for lambda using the quadratic formula, and we are guaranteed to get 2 eigenvalues because this matrix is over the complex numbers. So we'll find the eigenvalues using the quadratic formula, and there they are. They're ugly, but let's add them together anyway and see if we end up with the trace. So I've added the eigenvalues together up here, and luckily enough, those ugly square root terms that made them look all scary, they cancel, and we're just left with lambda 1 plus lambda 2 is the trace of A over 2 plus the trace of A over 2, which of course is the trace of A. So now let's multiply our eigenvalues and see if we end up with the determinant. So I've multiplied them here, and this looks ugly at first until you notice that it is of the form A minus B times A plus B. So when we FOIL this, instead of actually foiling it, we know we'll end up with A squared minus B squared. So that's what I've just written here, and that squaring, that square root term, gets rid of the square root, obviously, and you just end up with the trace of A squared over 4 minus the trace of A squared over 4 minus 4 times the determinant of A over 4. And that should be pretty obvious that we have the determinant of A right there. Okay, so part C asks us to verify that these two little theorems work for a specific example, and I've gone ahead and done that here. It's a pretty easy matrix, all 1s and 0s. The trace, as you can see right away, is 3. The determinant, you get the determinant by, I used a calculator online because I've done my fair share of calculating 3 by 3 determinants by hand, but essentially it just amounts to reducing the determinant to a series of 2 by 2 determinants, which we know the formula for. And then I found the eigenvalues also using a calculator, but you can do it by hand. It's just a mess. The characteristic equation ends up being cubic, so you have to use the cubic formula to find the eigenvalues, and no one wants to do that because the cubic formula is a mess. So I used a calculator. And so let's add our eigenvalues together. We can see that the i's will cancel, and we'll just be left with 3. And then, which is what we had as the trace, and let's multiply them together, and then we get, when we FOIL that right there, I left out the 1. You know, everyone knows that 1 is the multiplicative identity. So when we FOIL 1 minus I times I plus 1, we get I plus 1 minus I squared minus I. The i's canceled, but then we're just left with 1 minus I squared, and that's not 2 until you remember that I squared is -1, and then 1 minus -1 is 2, and everybody's happy. So that is part C. So an alternate proof for parts A and B, I just wanted to mention this because this is really the heart. This is the spectral theorem is the heart of what we're doing here. And the spectral theorem says that given any matrix, there exists an orthonormal eigenbasis for that matrix. And what that means is you can find the eigenvectors for that matrix and then re-represent the matrix with respect to some of those eigenvectors as basis for the vector space that that matrix is operating on. And when you do that, what happens is the matrix turns into a diagonal matrix with its eigenvalues along the diagonal. And of course, that's not obvious as to why that happens right away. The proof is fairly involved, but just trust me, that's what happens. And then once you apply the spectral theorem, it's really obvious that the trace of this matrix is the sum of its eigenvalues, and the determinant of this matrix is the product of its eigenvalues. So I just wanted to bring that up because the spectral theorem is very important, and I'm guessing it's going to be super important to what we're doing in quantum mechanics, because you always want to have, I'm guessing we're always going to want to have our operators represented diagonally. So yeah, that's it.